Hello students, welcome to the amazing platform of Physics Wallah. Welcome to the PW English channel, my dear students. Today we are on the last lecture of chemistry, electrochemistry, right? Yes. So today we are on the last lecture of electrochemistry, my dear students. What are we going to discuss today? Let's see. Today we will be discussing about a very important topic, which is Kohlrausch law, and also we will be practicing a lot of questions. So let's start this amazing session. Just to start this session, my dear students, we need to understand a few terms, and I know that you know those terms yourself, so you only have to revise them. So let's start. First and the most important is your, let's talk about it. Okay, so now let's discuss about this, my dear students. We will be talking about dilution. We will be talking about dilution. Let's talk about what does dilution mean. So my dear students, dilution actually means that adding more of your solvent. If you have a solution, you have a solute and you have a solvent, you only add more and more of your solvent and the number of moles of solute remains the same. You don't change the moles of solute, but you change the amount of your solvent. That is what is known as dilution. Let's take an example. Just for say, let's say we made a sugar solution and it is very sweet in taste, but I want to minimize the sweetness. What will I do? I'll add more of the water to it, right? Yes. So sugar was your solute and water is your solvent, and you added more of the solvent, and now the amount of solute, that is your sugar, is same, but the amount of your solvent, that is water, has increased, and this process is known as dilution, right? Yes. So I hope you are clear with this. What does dilution mean? Addition of solvent, keeping amount of solute same, keeping amount of solute same. Okay, perfect. Or you could say constant. I hope you're clear with this. Now let's move forward. Now, my dear students, why I told you this dilution concept? Because now we will be discussing the effect of dilution on the different types of conductivities we have studied. We have studied majorly three types of conductivities. The first is normal, your conductivity, which you represent by K, which is also known as kappa, right? Yes. Next is your, which is represented by this symbol, and this is your molar conductivity. And then we have equivalent conductivity. So now, my dear students, what are we going to understand is that what happens if we increase the dilution, what will the increase in dilution, how the increase in dilution will affect these three types of conductivities. One by one, we will be discussing about each and every part. So now, my dear students, when I talk about the normal first conductivity, that is K. Now, what is this conductivity? The definition of this conductivity is conductivity per unit volume, right? Yes. So this means that, let's say you have a container and let's say you have 1 liter of volume here. Now you have diluted it, and now let's say you have 2 liters of your solvent. You had, let's say, 1 mole of solute here. Until now also your solute will be still 1 mole. Now, you know that on dilution, what happens is, whatever your solute is, if it is electrolyte, we generally talk about electrolyte, it dissociates into ions, right? Yes. So, my dear students, in normal conductivity, if we are increasing the volume, what will happen? Actually, this means that conductivity per unit volume, this means that here you were just checking, let's say 1 meter cube, you were just checking that how many moles of your solute are present in a particular amount of volume, let's say 1 meter cube. So how many moles of solute were in 1 meter cube of volume? The more the number of ions, the more will be the conductivity. Now if you have increased the volume, so now what happens is your ions have a larger area to be present in. So this time, my dear students, when you check 1 meter cube volume, you will have comparatively lesser number of ions, and since you have lesser number of ions per unit volume, the conductivity has decreased, right? Yes. So this is how we say that conductivity actually decreases on dilution. It actually decreases on dilution. It actually decreases on dilution. Why? Because the number of ions per unit volume has decreased, because the number of ions per unit volume has decreased, and so your conductivity on dilution also decreases. Okay, perfect. We have studied this particular part. Now let's study the effect on molar conductivity, that is your lambda m. What is molar conductivity? Conductivity of 1 mole of electrolyte. Now my dear students, let's say you have 1 mole of your electrolyte. Okay, so you have a container here and you have 1 mole of electrolyte here. You just need to see that what is the conductivity of 1 mole of electrolyte. Okay, so initially you had, let us say, 1 liter of volume, and then let's say you had 2 liters of volume, and still you had 1 mole of electrolyte. Now, since it is the conductivity of 1 mole of electrolyte, be it 1 liter or 2 liter, your moles will remain the same. Yes, ma'am, mole will not change because you haven't increased or decreased the moles of your solute. So the conductivity of 1 mole of electrolyte will actually increase. Why? Because in this time, in 2 liters, the ions will have a larger area, a larger volume to be present in, and that is the reason conductivity actually increases, right? Yes. So in this particular case, my dear students, molar conductivity increases on dilution. Okay, so this is the point which you need to understand, that if you increase the volume, the ions will have a larger volume to be present in, and eventually their conductivity increases. So molar conductivity actually increases on dilution. Okay, so this is the next point which you need to write. Please pause the video and write it. Okay, let's talk about the equivalent conductivity. Now we will be talking about the equivalent conductivity. It is the conductivity of one equivalent of electrolyte. Now if you have understood the 1 mole of electrolyte concept, then obviously you have understood this, and we can write directly that equivalent conductivity increases with increase in dilution. I hope you've written this. Perfect. You can write this, my dear students. This is the concept which we need to understand. Okay, yes. So we have understood that normal conductivity actually decreases with increase in dilution, but your molar conductivity and equivalent conductivity actually increases with the increase in dilution. Okay, so now my dear students, till now we have understood everything. Now since I am talking about the electrolytes, I just want you to have a better understanding, or you take a small revision of the electrolytes. You have actually studied electrolytes in your 11th, but I know that you might have forgotten, so I'll just let you revise it. Let's talk about the other topic which we will be discussing is electrolyte. Okay, so now let's talk about electrolyte. So my dear students, electrolyte, majorly there are 2 types of electrolytes. First is your strong electrolyte. I am sorry. and then you have weak electrolyte. Now let's try to understand these. So now, my dear students, when we talk about strong electrolytes, actually your strong electrolyte dissociates completely in their aqueous solution. Whenever they are present in their aqueous solution, they actually completely dissociate, and that is the reason they are known as strong electrolytes. So which are strong electrolytes? They dissociate completely. They dissociate completely in their aqueous solutions. And if we talk about weak electrolytes, they dissociate partially in their aqueous solution. So if a weak electrolyte aqueous solution, so if a weak electrolyte is present, it will not completely dissociate, rather it will dissociate partially. Let's take an example. So now, my dear students, let's take an example. Let's say you have a strong base NaOH. It is a strong electrolyte, so it completely ionizes into N plus and OH minus ions. But if we talk about weak electrolytes, let's take an example. It is CH3COOH. Now when we talk about CH3COOH, my dear students, it does not dissociate completely, rather it dissociates partially, and that is the reason an equilibrium is attained and the dissociation is shown as this. CH3COOH is a weak acid, and that is the reason it is a weak electrolyte. Okay, now let's take a few examples so that you will be very clear with the concept. So now, my dear students, when you talk about strong electrolytes, all the salts, strong acids and strong bases are your actually strong electrolytes. If you talk about weak electrolytes, my dear students, your weak acids such as CH3COOH, weak bases, example is NH4OH. These are, my dear students, your weak electrolytes. They do not dissociate completely. But strong acids, let us say example HCl, strong base NaOH. If you talk about salts, let's take an example NaCl. In fact, all salts are strong electrolytes. Okay, so this is what we need to understand about the electrolytes, strong electrolytes and weak electrolytes, because next topic is related to this. So pause the video, write it, and then we'll move forward. Okay. I hope you have written. Now, how are we going to do it? Perfect. I hope you've written it. Now, let's move forward, my dear students. Now, we will be plotting a little of the curves. Now, we will be discussing whatever we have studied till now, the dilution concept with the electrolyte concept. Okay. So, now, my dear students, if you see, you can see a plot versus equivalent conductivity and root of C. What is C here? C is your concentration. Let me tell you, C is the concentration. Okay, so now we have to plot a graph. So let's plot a graph, my dear students. We need a straight line. Okay. So now the plot will be equivalent conductivity versus root of concentration. So now, my dear students, you need to understand that if we move from here to here, your actually concentration is increasing. And since this side, my dear students, your concentration of the solution is increasing, can I say that the dilution of the solution is decreasing? Because more the dilution, lesser is the concentration. You have studied this in your concentration terms. I just made you understand that in the solutions chapter. So we can say that your dilution here in this side is actually decreasing. right? Yes. But if I talk about this part, if I move from this direction to this direction, what is actually happening? Your concentration of the solution is actually decreasing. If concentration is decreasing, this means that dilution is increasing. So I can say here dilution is increasing. So now, my dear students, just try to understand that this is your 0 point, and since at this particular point your concentration will be 0, this means that this is the point where you have infinite dilution. Though it is never possible, but still, if we talk about this 0 point, this is something where concentration is 0. So here your dilution is maximum, and we call it as infinite dilution. Okay, perfect. I hope you're clear with this. Now what I want to tell you is that when the plot was drawn, now if you talk about the equivalent conductivity, what do you say? Whenever we increase the dilution, equivalent conductivity actually increases. We studied that, and my dear students, it increases in such a manner. It increases in such a manner. Okay, this is the way your concentration, your molar equivalent conductivity increases. Okay, so we have understood this, that as we are increasing the dilution, the equivalent conductivity is actually increasing. But when this plot was drawn, my dear students, you can see that this particular part is still empty. You don't have a line here because scientists could not achieve that infinite dilution part, and they cannot measure the equivalent conductivity there. So what they did, they made a plot like this, and they saw that it is a straight line with a negative slope. So what they did was the best part. They actually wanted to calculate the equivalent conductivity at infinite dilution anyhow. So they extrapolated this part. They extrapolated this part. Now, when you extrapolate this part, my dear students, you get a point here. You get a point here, and this point is actually the point where you can see what will be the equivalent conductivity if you have infinite dilution. So, they extrapolated the graph and calculated the equivalent conductivity at infinite dilution for strong electrolytes. Okay, I just wanted to tell you this plot is for strong electrolytes. Okay, we are talking about strong electrolyte. Later we will be talking about weak electrolytes also. Okay, so this plot is for strong electrolytes, and for strong electrolytes they extrapolated the plot, and they found out that what can be the, for different strong electrolytes, different plots will be drawn, and obviously the equivalent conductivity will also be different, but we can see that the nature of the graph is similar. That is a straight line with a negative slope. So what they called this point as lambda m naught or lambda m infinite, is we are talking about equivalent. So they called it equivalent. I'm sorry. So they called it as equivalent conductivity naught or equivalent conductivity like this. What does these symbols mean? These symbol means that equivalent conductivity at infinite dilution or in limiting equivalent conductivity. These are the two names which means the same thing, but in your books these are mentioned something like this. So now let's write what all symbols represent. So my dear students, C is your concentration, lambda E is your equivalent conductivity, lambda E naught or lambda E infinite is your equivalent conductivity, at infinite dilution, or you can say it as limiting equivalent conductivity. Both of them means the same thing. Okay, yes. I hope you're clear with this. Okay, so this is how we can calculate the equivalent conductivity of strong electrolytes at infinite dilution. And same is the case for the molar conductivity for a strong electrolyte. So the molar conductivity graph is your homework. You have to try that yourself. Exactly the same. Exactly the same. Just change the symbol lambda E to lambda M. Okay. Pause the video, write it, and then we'll move forward. Okay. So now my dear students, scientists told that there was an equation which was known as Debye equation. That is lambda E is equal to lambda E naught minus A root C, where you know the symbols. A is a constant value. So all the strong electrolytes actually follow this equation. All the strong electrolytes actually follow this equation. Okay, so just a second, I am sorry, yeah, this equation. So all the strong electrolytes follow this equation, and the plots which you see are according to this equation. Okay, yes, so you can use this equation and find out whichever factor you have been asked. So this was all about the strong electrolyte equivalent conductance with respect to the concentration. I hope you're clear. So now let's move forward. You can pause the video, write it. Let's move forward. Now we will be talking the same. We'll be drawing a plot for lambda, that is equivalent conductivity versus root of concentration for weak electrolyte. This time we will be talking about the weak electrolyte. Now let's try to understand this. So again we have to plot a graph. Perfect. This will again be your equivalent conductivity, and this would be root concentration. I hope you know this side the concentration actually increases and your dilution actually decreases. This is your 0 point. Here, my dear students, you have infinite dilution. Okay. Now, when we talked about a weak electrolyte, you know that it doesn't dissociate completely. If doesn't ionizes or dissociates completely, so its conductivity cannot be measured very easily like for the strong electrolytes. So my dear students, for this particular part, we need to understand one more important part, which was known as Debye-Huckel-Onsager equation. Sorry, for Oswald dilution law. I am sorry, Oswald dilution law. Now, what does Oswald dilution law says, my dear students? Oswald dilution law actually says that as you increase the dilution, a particular electrolyte's ionization keeps on increasing. The more the dilution, the more the electrolyte will ionize. And it is majorly applicable to weak electrolyte because strong electrolytes actually completely dissociate. So the increase in dilution actually helps your weak electrolytes to ionize more and more. Okay, so Oswald dilution law actually said that increase in dilution increases the ionization of an electrolyte. So from this I can say that if I increase a weak electrolyte's dilution, obviously it will ionize more, and if it will ionize more, then the conductivity will keep on increasing. Its equivalent conductivity will keep on increasing, right? So we will be using this. If you want to write it, you write it, and then we'll move forward. Okay, I hope you've written it. Now I know that in this particular direction your dilution is increasing and your concentration is decreasing. So this means that more the dilution, more will be the ionization of the weak electrolyte, and more I will get the equivalent conductivity. Using that concept, when the scientists plotted a graph, what did they observe? They observed a plot something like this. So now this was a very challenging task, because if you see here, my dear students, if you see here, this actually goes to parallel, but in the case of strong electrolyte we could extrapolate and we could see what would be the equivalent conductivity at infinite dilution. But if I increase it, if I extrapolate it, it is parallel to the equivalent conductivity axis, and I can never ever get the equivalent conductivity of a weak electrolyte at infinite dilution. And this was a big problem, because we cannot calculate the equivalent conductivity of a weak electrolyte at infinite dilution. Okay, so this was a major drawback, and we needed some solution to calculate the equivalent conductivities of the weak electrolytes as well. Okay, yes, perfect. So if you want to write it, just write it, my dear students. Perfect. I hope you have written it. You have paused the video, you've written it. So now, this is your homework. You have to plot the graph. You have to plot the graph for molar conductivity versus concentration for strong electrolyte. It will be exactly same as equivalent. Okay, just draw it so that it will be revised. And same for weak electrolyte. Okay, perfect. I hope you have written this. This is your homework, so I hope you've written it. Now let's move forward. So now, my dear students, here are a few points which you need to understand about weak electrolytes. You can pause the video and write it. In case of a weak electrolyte, the increase in equivalent or molar conductance is more pronounced with the dilution. The degree of ionization of a weak electrolyte increases with increasing dilution, and this was the Oswald dilution law. I gave you this, so just write it and then we'll move forward. I hope you've written it. Perfect. Now let's move forward, my dear students. Now we will be talking about Kohlrausch law. What is Kohlrausch law? Infinite dilution, independent migration of ions. Kohlrausch law of independent migration of ions. Actually, my dear students, Kohlrausch gave a solution to a problem. He gave a solution to a problem how we can calculate the weak electrolytes equivalent conductivity at infinite dilution and molar conductivities at infinite dilution. And what was the solution? Now we will be studying that. So let's start this. If we talk about Kohlrausch law, what did Kohlrausch said? Let's take an example. Let's take a electrolyte. Let's say I have taken NaOH. So what does Kohlrausch say? Kohlrausch says that when you increase the dilution of electrolyte, you know that the ions ionize more, right? Let's say I have increased the dilution to such extent that your Na plus ion has come here and your OH minus ion has come here, and there is no interaction between them. Why? Because they are far away from each other. We have increased the dilution to such an extent that there is no effect of one ion on the other. Now they don't have any interaction, they are on their own, and at this particular point you can calculate their conductivities. So you can calculate the conductivities of individual ions. You can calculate the conductivities of individual ions at infinite dilution. So from here I can calculate the equivalent conductivity at or the limiting conductivity of Na plus, let's say it is X. So my dear students, here also limiting equivalent conductivity of OH minus, let's say it is Y. Now they have no interaction with each other. So what Kohlrausch did? Kohlrausch took an electrolyte, let's say a strong electrolyte, and it increased its dilution to such an extent that the ions were far away from each other and they don't have any interaction to each other. Now he calculated their individual limiting molar conductivities or limiting equivalent conductivities. Yes, for strong electrolytes we can calculate. So he calculated for the individual ions, and what he said was that these limiting molar conductivities at infinite dilution of the individual ions are their fingerprint. That is, it is a specific value which cannot change, which will never change. This means that this X value for Na plus is its own, be it NaOH is present in NaOH or be it Na is present in NaCl. The equivalent conductivity or the molar conductivity at infinite dilution of Na plus in both of them will be X. Yes, OH minus and Cl minus will have different values, but the value for Na will be same in both. The limiting value, that is the equivalent of molar conductivity at infinite dilution. So this was the Kohlrausch law, that just take these strong electrolytes, dilute them to such an extent the ions are separated from each other, calculate their individual molar conductivities at infinite dilution or equivalent conductivities at infinite dilution. So this is what Kohlrausch law said, and this is what Kohlrausch law of independent migration of ions is called. So let's try to write the definition. So my dear students, Kohlrausch law said that the value of limiting molar, I am talking about molar first, molar conductivity of an electrolyte, I'll make you understand this definition as well, of an electrolyte is the sum of limiting molar conductivities of their individual ions multiplied by their stoichiometric coefficients. Now let's understand what does this mean. So my dear students, what does this mean is, let's say you have an electrolyte AXBY and you need to calculate its molar conductivity at infinite dilution. So Kohlrausch says that the limiting molar conductivity of an electrolyte will be equal to the sum of limiting molar conductivities of the individual ions, because that is their own value which is unique to them. It will be the sum of the limiting molar conductivities of each ion multiplied by its stoichiometric coefficients. So let's write it. This means that X into molar conductivity at infinite dilution of AY plus Y into molar conductivity at infinite dilution of Bx minus. So now you will be like, ma'am, do we need to memorize this formula? It is very difficult. So I'll give you examples. You need not memorize the formula. You can just understand how to apply this. Okay, so let's talk about the limiting molar conductivity of NaOH. So if we talk about NaOH, we know that there is no stoichiometric coefficient coming here. It doesn't have any number here. So the limiting molar conductivity would be of Na plus limiting molar conductivity of OH minus. Okay, as simple as that. Let's make it a little more complicated. Let's say it is Na2SO4. What does this mean? So you will have 2 here, so you have to multiply it by 2, then molar conductivity of Na plus. Then for SO4 2 minus, you don't have anything, so this will be 1. So 1 into molar conductivity at infinite dilution of SO4 2 minus. So you can just write it like this. You need not memorize the formula. Okay, so don't be confused if I have written 0 somewhere or infinite. It is one and the same thing. Okay, I am telling you this again and again. So now let's complicate this a little more. Let's say we have lambda m naught of Ca3 PO4 whole twice. So if you need to write the molar conductivity of this will be 3 into molar conductivity at infinite dilution of Ca2 plus you have 2 into molar conductivity at infinite dilution of PO4 3 minus. Okay, every ion has its individual, its fingerprint value, its Aadhaar card value for their molar conductivity at infinite dilutions. Okay, so this is how you write this. I hope you're clear with this. Pause the video, write it, and then we'll move forward. Okay, I hope you've written it. Now let's write the Kohlrausch law for equivalent conductivity. There is a little change, everything else is same. The limiting equivalent conductivity of an electrolyte is equal to the sum of limiting equivalent conductivities sum of limiting equivalent conductivities of the ions. Okay, so now let's understand this. I'll give you another one formula. Let's say you need to calculate the equivalent conductivity of AXBY. This will be equal to equivalent conductivity at infinite dilution of A plus equivalent conductivity at infinite dilution of B minus. You need not write the stoichiometric coefficients here. For equivalent, you don't need to write the stoichiometric coefficients. Okay, this is the major difference between the two. This is the major difference between the two. I hope you're clear. So now let's take a few examples. So we'll have equivalent conductivity, limiting equivalent conductivity for NaOH. This will be equivalent conductivity limiting for Na plus OH minus. Next you have, let's say, limiting equivalent conductivity for Na2SO4. This will be equivalent conductivity for Na plus you will have equivalent conductivity limiting for SO42 minus. You need not write the stoichiometric coefficients. Equivalent conductivity for, let's say, Ca3PO4 whole twice. Equivalent conductivity for Ca2 plus limiting equivalent conductivity for PO4 3 minus. So this is how you calculate the limiting equivalent conductivities of the various electrolytes. I hope you are clear with this. Okay, now let's move forward. Pause the video, write it, and then we'll move forward. So now whatever we have studied, it is written here, just go through them. Okay, the equivalent conductance of an electrolyte has its maximum value at infinite dilution. I hope we know that, and it is constant for a given electrolyte. It is called the equivalence conductance at infinite dilution. Any electrolyte, strong or weak, will be 100% ionized at infinite dilution. At infinite dilution, the interionic attraction, that is the attraction between the ions, is 0, and each ion migrates independently. Okay, so pause the video, write it, and then we'll move forward. Next point. Now, each ion can contribute a fixed value towards the equivalence conductance of the electrolyte, and this is known as ionic equivalence conductance. It is constant for a given ion and different for different ions. One important thing which you need to know is, we in the last class or last to last class, we studied that lambda m is equal to lambda equivalent into n factor. I made you understand how to calculate the n factor as well. So similarly, my dear students, you can say that molar conductivity at infinite dilution will be equal to equivalent conductivity at infinite dilution into n factor. So you need to know this formula, because if you know one conductivity, you can calculate the other just by multiplying it to the n factor. Okay, so you just write it, and then we'll move forward. I hope you've written it. Now let's move forward. Let's try a question and try to understand how to do these problems. So the question says that molar conductivity, limiting molar conductivity of CaSO4 you have to calculate. Also you have to calculate the equivalent conductivity. you are given the limiting molar conductivities of the ions. So first we can calculate the limiting molar conductivity of CaSO4, which will be equal to 1 into limiting molar conductivity of Ca2 plus 1 into limiting molar conductivity of SO42 minus. What are the values given to you? 119 plus 160. So this will be 9, 617 and then 279. Okay. So this is the molar conductivity. You can write Simon centimeter square mole inverse. Okay, perfect. I hope you're clear with this. Now let's move forward. Just a second. Write it. Try to do this question. Okay. I hope you've written it. Now, you have to calculate the equivalent conductivity as well. I hope all of you remember that molar conductivity limiting is equal to limiting equivalent conductivity into the n factor. Now, let's see what is the n factor for this particular electrolyte, CaSO4. How do we calculate the n factor? Total positive charge or total negative charge. How much is the total positive charge? 2 plus. And how much is the total negative charge? 2 minus. So, n factor is 2. So, you can calculate your equivalent conductivity will be molar conductivity limiting upon n factor. So this means that 279 upon 2, which is 139.5 Simon centimeter square equivalent inverse. Okay, so this is how you can calculate the equivalent conductivity, limiting equivalent conductivity. Okay, I hope you're clear with this. You can pause the video, write it. Let's try another question. I hope you've written it. Next question, my dear students. You have to calculate equivalent conductivity limiting and limiting molar conductivity. You are given a few values. Now see what are you given. You are given the limiting equivalent conductivities of the individual ions. So first you can calculate the limiting equivalent conductivity. Okay. So limiting equivalent conductivity of BaCl2 will be equal to limiting equivalent conductivity of Ba2 plus limiting equivalent conductivity of Cl minus. We need not multiply with the stoichiometric coefficients. So this will be 63.5 plus 76, which is equal to 0.5. Then you'll have 76. So you will have okay, 0.5, then you have 9, and then you have 7, 3, 13. 139.5 Simon centimeter square centimeter square equivalent inverse. Now you need to calculate the limiting molar conductivity as well, and we know that limiting molar conductivity is equal to limiting equivalent conductivity into n factor. Just a second. Yes. Okay, fine. So now you have to calculate the limiting molar conductivity of BaCl2. This will be equal to equivalent conductivity is 139.5 into n factor. What is the n factor, my dear students? For BaCl2, total positive charge is 2 plus, total negative charge is 2 negative. So n factor is 2. So just multiply it and you will get your answer. Okay. Yes. And the value would be Simon centimeter square mole inverse. So this is how we will be solving these types of questions. I hope you're clear with this. Pause the video, write it, and then we'll move forward. Okay. So now my dear students, what are we going to discuss? So now we will be discussing, we have understood what is Kohlrausch law and how to apply the Kohlrausch law. But we need to understand a few applications of Kohlrausch law, how Kohlrausch law helped us in calculating various different things. So the first is, let's write the heading as applications. So the first application of Kohlrausch law was that it helped in calculating the degree of ionization of an electrolyte. Degree of ionization of an electrolyte. So it actually helped to calculate the degree of ionization of an electrolyte. How? Let's write the formula. You need to know this formula, where alpha is the degree of ionization. This is the degree of ionization. Okay. So degree of ionization is given by lambda m upon lambda m naught. This is the formula for calculating the degree of ionization. Okay. So this is how you calculate the degree of ionization. If you have molar conductivity and if you have limiting molar conductivity, you can calculate the degree of ionization of a particular electrolyte. Okay, so this was the first application. If you want to, of course you have to write it, so just write it and then we'll move forward. Let's talk about the second application. A second application was it helped in calculating the dissociation constant of weak electrolytes. So in calculating dissociation constants of weak electrolytes. Now let's talk about how it helped in calculating the dissociation constant of weak electrolytes. Let's take an example of weak electrolyte which I have told you, some weak acid. So I am taking a weak acid which is CH3COOH. It dissociates as CH3COO minus and H plus. This is your dissociation constant. Now let's say at t is equal to 0 time, you had some C concentration of your weak electrolyte. So there was no dissociation happening because it was the starting. Now we know that alpha is the degree of ionization. Alpha is the degree of ionization. It is the degree of ionization for your weak electrolyte. Okay. Yes. So at some t is equal to t time, when some dissociation might have taken place and an equilibrium has reached, obviously C minus C alpha of your acid is left. C alpha of your acid has ionized. So C alpha of this and C alpha of this has been formed. Since Ka is the dissociation constant, it is also the equilibrium constant. You can say that Ka is equal to concentration of products divided by concentration of reactant, C minus C alpha. So Ka will be equal to C square alpha square upon, let's take C common, 1 minus alpha. C we can cancel, so this will be C alpha square upon 1 minus alpha. Since it is a weak acid, since my dear students CH3COOH is a weak acid, I know that this degree of dissociation or this degree of ionization is very small as compared to 1. So 1 is much larger than alpha. So 1 minus alpha can be considered nearly as 1. Okay. So your Ka value comes out to be C alpha square. So this is how you calculate the, dissociation constant. You can calculate it as you have concentration, you know alpha is equal to lambda m upon lambda m naught whole square. So this is how you can calculate the dissociation constant. Okay. So this was the application, second application of Kohlrausch law. You can write it and then we'll move forward. I hope you've written it. Now let's move forward. Next application, which is your third application, my dear students, it helps in calculating solubility and solubility product of sparingly soluble salts. Sparingly soluble salts. Okay. So now let's say you have a sparingly soluble salt AX. Let me give you a normal example and you will understand it. Let's say you have a sparingly soluble salt AgCl. So KSP will be the solubility product. Okay. This will give you Ag plus and Cl minus. So here, my dear students, KSP is the solubility product and your here S will be the solubility. Okay, I hope you're clear till now. Now, what happens is, how do you calculate the solubility product for the sparingly soluble salts? Here, my dear students, you just have to understand it. I'll give you 2 to 3 examples and I'll make you understand. Whenever you talk about solubility, let's say its solubility is S, then its solubility will also be S. So, when you write KSP, what you need to do is write the solubility of Ag plus, which is S, raised to the power its stoichiometric coefficient, which is 1, into solubility product of the other and raised to the power stoichiometric coefficient. So KSP here, my dear students, is equal to S square. Okay, I hope you are clear till now. This was easy. Now let's complicate the things a little more. Let's take another example. You have Na2SO4. Now, if you have a sparingly soluble salt, something like this, then this will be your KSP value and you will have 2Na plus and you will have SO4 2 minus. Okay. So, again, I know that solubility is S and KSP is the KSP solubility product. So, this time, my dear students, since here it is 2, so it will be 2S. Since here 1, so this will be S. Now, when you write the KSP value, how do you write the KSP value? You have 2S, write 2S raised to the power its stoichiometric coefficient, which is 2. Here you have S raised to the power its stoichiometric coefficient, which is 1. So, this is 4S cube. So, the KSP value is equal to 4S cube. This is how you write the solubility products. I'll give you one more example and you will be clear with the concept. Let's say you have a sparingly soluble salt of Ca3PO4 whole twice. Okay, so this will give you something like KSP here. It will be 3Ca2 plus and you will have 2PO4 3 minus. So if you write the solubility here, since it is 3, so this will be 3S. Since here it is 2, so it will be 2S. If you want to write the solubility product, then KSP will be equal to, you have 3S raised to the power its stoichiometric coefficient, which is 3. You have 2S raised to the power stoichiometric coefficient 2. So 27S cube into 4S square, which is 27 into 4S raised to the power 5 is the solubility product. Okay. This is how you calculate the solubility product. Okay. Now, you all know that molar conductivity is equal to K into 1000 upon C concentration. So, instead of this concentration, my dear students, you can write the solubility. The unit of solubility is actually moles per liter. It is actually the concentration units. So, you can write S here. When you write S here, so you can calculate S as K into 1000 upon molar conductivity. Once you calculate this, put this into the KSP value and you can calculate the solubility product as well. So this was the application for the solubility product and solubility. Okay. So if you want to write it, pause the video, write it, and then we'll move forward. I hope you've written it. Now let's move forward, my dear students. Let's understand the fourth and the last application, which is of the most importance. What is the most important application? In the starting of the chapter, we saw that we were unable to calculate the limiting molar conductivities for weak electrolytes. But using the Kohlrausch law, we can calculate the limiting molar conductivities of weak electrolytes as well. So this was the most important application in calculating the limiting molar conductivities. Can I say limiting conductivities? Because you can calculate molar as well as equivalent. So, limiting conductivities of weak electrolytes. Now, let's understand how. Okay. So, now my dear students, when you talk about a weak electrolyte, I'll be making a example on my own. So, just bear with it. Let's say you had a strong let's say you have AX, B, Y and X, Y strong electrolytes. You have these strong electrolytes. Yes, you can dilute them to the infinite dilution and you can calculate their individual molar conductivities. Yes, you can calculate. So can I say that the molar conductivity, limiting molar conductivity of AX, let's say it is equal to X. This is what we know. Let's say limiting molar conductivity of By is equal to Y, and limiting molar conductivity of Xy is equal to Z. Okay, see now this is something that we can calculate from the graph because these all are strong electrolytes. Okay, and let me tell you that your let's say you have AB as your weak electrolyte. Okay, so AB is your weak electrolyte. So you have to calculate actually the limiting molar conductivity of AB. So how will we do this? Okay, this is your task to do. So now let's see how are we going to achieve this. Okay, so you know that these are strong electrolytes. You will calculate their individual conductivities as X, Y and Z. From Kohlrausch law, you know that the molar conductivity of this is limiting of A plus, or let's say A plus limiting molar conductivity of X. Okay, this is equal to limiting molar conductivity of B plus limiting molar conductivity of Y. This will be limiting molar conductivity of X plus limiting molar conductivity of Y. Right? Yes. This is something that we know. What we have to calculate is, we have to calculate limiting molar conductivity of AB. See, I know that AB is a weak electrolyte, so I don't know direct value of AB. But I know that if I dilute it to the infinite dilution, according to Kohlrausch law, this should also be equal to A plus limiting molar conductivity of B. This should be equal to this, right? I know this. Now, my dear students, using these three equations, can we somehow calculate this? Yes, we can calculate this. How? Let's say this is 1, let's say this is 2, and let's say this is 3. So now, my dear students, let's check. You know, you want A part, so you want first equation, so let's add first equation. You want B, so let's add it to the 2 part, minus. Now, when you will add these two equations, my dear students, when you will add these two, you will get A and B, but you will also get X and Y. But you don't want X and Y. So I can subtract this third equation, then X and Y will be cancelled out. Yes. So minus 3. This will give me the value as X plus Y minus Z. And this is how I can calculate the limiting molar conductivity of a weak electrolyte. Because I know that when, according to Kohlrausch law, when you will keep the ions at infinite distance from each other, their limiting conductivity is their individual value, be it in a strong electrolyte, be it in a weak electrolyte. So we just calculated the molar conductivity of weak electrolyte using the Kohlrausch law, and this was the biggest application. Okay, so you can write it and then we'll move forward. I hope you've written it. Now let's try to solve a question. Just a second. Now let's try to solve a question. You have a question. Try the question, my dear students. The question says that find the limiting molar conductivity of BaOH whole twice. You are given electrolytes and you are given their limiting molar conductivities. So I know that limiting molar conductivity of BaOH whole twice will be equal to limiting molar conductivity of Ba2 plus 2 into limiting molar conductivity of OH minus. So this is something that I need. Now let's try to write them in an equation. You can say limiting molar conductivity of Na plus limiting molar conductivity of OH minus. This is equal to 248. I hope you can write it something like this, right? This will be your first equation. Let's write the second equation. The second equation will be limiting molar conductivity of NaCl. This will be limiting molar conductivity of Na plus limiting molar conductivity of Cl minus, and this is equal to 126. Next is limiting molar conductivity of BaCl2. This will be equal to limiting molar conductivity of Ba2 plus 2 into limiting molar conductivity of Cl minus. This is equal to 280. This is your second equation and this is your third equation. You need Ba2 plus. You have Ba2 plus. So you will have to first take the third equation. Then you need 2 of OH minus. You have 1 of OH minus. So you will have to multiply first equation by 2. Now, when you will multiply this equation with 2, you will get 2, 2, and this will also be into 2. Right? Now, this is addition, so this and this will be added, and this you have to subtract because you need to, you don't need Na plus and you don't need Cl minus. But when you will subtract it, my dear students, you have 2 of Na plus, so you have to multiply this also with 2 and you will have to subtract this whole equation. I hope you are getting this. So this means that minus 2 into 2. So let's try this. This 2 minus will be subtracted with this, and you have 2 OH minus, you want that, and then Cl minus will be subtracted by TCl minus because you will have 2 here as well. Okay. So this means that third equation is 280 plus first is 248 into 2 minus second equation is 126 into 2. So just solve this and you will get the molar conductivity of BaOH whole twice. So this is how you will be solving this particular question. I hope you're clear with this. Perfect, my dear students. Just write it and then we'll move forward. Let's try another question. The question is on your screen. The conductivity of 0.01 molar CH3COOH is, okay, so you are given the concentration as 0.01 molar, and also you are given the conductivity as Simon centimeter inverse. So you are given K value as 3.9 into 10 raised to the power minus 5. Find the Ka and alpha of lambda if lambda m naught is given. Also you are given infinite lambda m naught, which is 390. See, you need to calculate alpha. Alpha is equal to lambda m upon lambda m naught. I have lambda m naught, but I don't have lambda m. How can I calculate lambda m? Lambda m is given as K into 1000 upon C. So K value is given 3.9 into 10 raised to the power minus 5 into 1000 upon concentration, which is 0.01. This will be 3.9 into 10 raised to the power minus 2 into 10 raised to the power 2. So this is equal to 3.9. So lambda m is Simon centimeter square mole inverse. This is 3.9. So you need to calculate alpha. So 3.9 upon 390. One upon 100. See, so your alpha is 0.01. Okay, you need to calculate Ka value. You know that Ka for a weak electrolyte will be nearly equal to C alpha square. You have C value, which is equal to 0.01 10 raised to the power minus 2 into alpha is 10 raised to the power minus 2 whole square. So this is 10 raised to the power minus 2 into 10 raised to the power minus 4, which is equal to 10 raised to the power minus 6. So this is your Ka value, that is the dissociation constant value. Right? Yes. So this is how you use the Kohlrausch law and calculate different things. So this is how you will be solving the questions. Okay. So with this, let's end our session, my dear students. I hope you have understood everything. We have covered a lot of things in this particular topic, and it was a very interesting topic. So a lot of questions are actually asked from this part, so you need to practice a little more. Try to practice and be perfect with whatever you do. We'll meet in the next session with a new chapter. Till then, keep studying. Thank you so much. All the very best.